Okay, so the next couple of videos are going to be on the Y wound and the delta wound dual voltage three-phase motor. And an example of a dual voltage three-phase motor would be something like this. So I've done a quick Google search here, and I've come up with this image here. This is from a great site, Electrical Engineering Portal. If you have a chance, go and check out their stuff. Great site for electrical theory. Capacitors, transformers, anything that's there. They got really good articles. Okay, so this is from a three-phase motor here, and it's a dual voltage in that you can see that you can hook it up to 2.8 or you can hook it up to 460, right? So 2.8 to 230 and then 460, right? So the two voltages are usually 2.8 and then 416 for the other voltage. Corresponding with those voltages, if you have a lower voltage, then it requires more current in order to create the same horsepower, right? This is a 7.5 horsepower motor. If you have a higher voltage, it uses a lot less current in order to create the same amount of horsepower. Either connection here is going to give us the same horsepower output. So the 2.8 connection in parallel was going to give us 7.5 horsepower maximum, and then this one at 416 and the series connection is going to also give us 7.5 horsepower output. Okay, so let's take a look at the Y-wound motor first. And the first thing we need to do is we need to put in our labels for each of the windings here. Now, if Ted's watching this, he'll cringe. Ted is my guru. Anything that anything that comes out of my mouth is basically just me trying to extrapolate on what Ted has in his mind. He's my guru at work. And so if he's watching this, he'll probably cringe because I'm going to go in a clockwise direction because that's how my brain remembers how to do this diagram. And he'll say, no, it's got to go counterclockwise because in Canada, the convention is to go counterclockwise. But I'm going to go clockwise just to be a rebel. So here, we're going to start off on the outside. So this guy right here is going to be T1. This guy right here is going to be T2. This guy is going to be T3. And you can see how I'm sequentially going around. And I call this the toilet bowl effect in class, because we're just starting here at T1, going around to T2, T3, and then doing this toilet bowl effect right into the center. Okay, this is a 9-lead dual voltage motor. So after T3 is obviously T4. This is T5. Following is T6. Then we got T7, T8, and this is a 9-lead motor, so this is T9. And that's where we stop, right? In the background here from the manufacturer, this guy is T10, right? This here is T11, and this guy right here is T12. But they're already connected up from the manufacturer. So let's connect that up because we have no access on the 9-lead motor to those connections. This guy is a Y connection. So 10, 11, and 12 are already connected from the manufacturer and we have no way to get to those connections. Okay, we're going to do the low voltage connection. So what I'm going to do is I'm going to feed this motor, and the way that we feed this guy is the same as any motor. So we're going to bring line 1 into T1. We're going to bring line 2 into T2. And then we're going to bring line 3 into T3. Just like any motor. So if we're bringing the same connections in, right, line 1, line 2, and line 3, like we do with a standard motor, then it follows that to reverse this motor, all we have to do is just switch any of these two incoming conductors and the motor will go in the opposite direction. Okay, now, in order to connect into a lower voltage, in this case, remember that the voltage was 208 volts, right? So, in order to connect in there, the rule is that the lower voltage always means parallel connection. So we're going to put parallel here for our lower voltage connection. And anytime we're connecting up to the higher voltage source, then we need to connect the windings in series. Now, in doing this diagram, you may want to do a separate diagram below just to follow through and use as a guide, right? So let's do that below. Let's grab a black conductor here, and let's just create a quick little diagram down here. And what we're going to do, you can see that there are 2 different windings per phase, right? And we've got to connect those bad boys in parallel. So we're going to do a different diagram here, because maybe that diagram above, if I just rock through it, maybe it's not going to make all that much sense to you. So, and to me, I often have to do this separate diagram here. That looks like garbage. Hang on. Putting these guys in parallel, and then I can go off of this guy to do my connections above. Okay, so again, I've got, let's just put T1, right? And if we look at these guys, we're going to go around. Now, don't worry about the placement of each of these guys. So T1, T2, and then what? T3 over here. So don't worry if I have this above or below. It's in parallel. It's connected to the same piece of wire. It doesn't matter if T3 is here or here. Okay, the next one is T4. Then on the other side of the T2 winding, we have T5. Then we got T6, right? Then we have T7, then T8, T9, and then remember that T10, T11, and T12, right? Let's put those guys in, but we'll just put them just faintly, right? So T10, T11, and T12, they're there, but we can't get to them, right? They've already been connected in from the manufacturer. So based off of this, we can now finish off our diagram above. So let's just make this, see if we can compress this a bit. And then there we go. We can see everything on the screen. So let's see. In paralleling these guys up, it looks like 1 and 7 are going to be jumpered together. So let's do that. Let's jumper 1 and 7 together. Okay. We can see here that 2 and 8 are jumpered together. Beautiful. And then here we can see that 3 and 9 are at the same potential. So again, 3 and 9. Maybe I'll put that guy over here just so it's not in the way when I do my last connection there. Okay. So hopefully you're following along. We got T1 and T7 at the same potential, T2 and T8 at the same potential, 3 and 9 at the same potential. And now it looks like 4, 5, and 6 have to all join together, right? 4 is joining in with 5, is joining in with 6. So they always do this in their diagrams. They take 4, they bring it around here, they grab number 5, right? And then that ties in with 6. And that jumper's just over this connection right there. Okay, so 4, 5, and 6 are at the same potential. Now, in addition to this diagram right here, this might even mess you up. So the way that it's actually drawn, let me just move this over a touch so I can have a little bit more space to work with. Okay, so now we move that over, we got a little bit more room to play with, because some of you are looking at this diagram and saying, well, that's a little bit messed, because on this diagram, 4, 5, and 6 are not tied together with 10, 11, and 12, but over here, it looks like they are. So they're not. I mean, if we look at the way that this guy is connected up, we've got this winding here. So let's put one of the windings here. Easy now. What happened there? Okay, so one set of windings is like this, right? So we've got a Y connection like this. Then we've got a separate connection over here. Whoa, what is going on? I was doing so well too. There we go. Okay, so we've got 2 separate Y connections, and this is the way that it's actually connected up. So if we take a look here, we've got T1, right? The other side of T1 is T4. Then we've got T2 over here. The other side of T2 is T5. Then we got T3, and the other side of T3 is T6, right? So there we've got, excuse me, 4, 5, and 6 connected together in that Y connection there, right? On the other side, then we've got T7, T8, and T9. Those are the only ones that we can get to. But again, in the background, we got T10, right? Can't even make that out. Pen's not working for me today. So T10, right? Over here we got T11. And then over here we got T12. So we can't get to those connections there. But we know that 10, 11, and 12 are brought together. So when we look at the actual connections and we finish this guy off, let's draw this maybe in a blue here, right? Then we've got line 1 going to T1 and to T7. Then we got line 2, and we'll just draw line 2 over here. Line 2 is going to T2 and T8. And then line 3 is going to T3 and where else is it going? It's going to T3 and T9, right? So T3 and T9. We'll just jump over here, right? So that's the way that these guys are actually hooked up. So whatever drawing works for you, right? This one works for most people. They can picture it in their head. This one works for others. It's a little bit easier, but it does make that little misnomer that the Y's are actually connected together. What happens is that you have two different Y's that are superimposed on each other, and no connection to the neutral because they're balanced lows, right? There's no requirement for that star point to be tied in with that star point there. Excellent. So now we're at a point where we can finish off this chart below. We're doing the low voltage connection here in parallel. And it looks like, if we just zoom in here a little bit, that for the low voltage, line 1 is tied in with T1 and T7. So we can put T1 and T7 there. Line 2 is going to T2 and T8. Line 3 looks like it's tying in with T3 and T9. And in order to create that Y connection, we have to join 4, 5, and 6 together. So T4, T5, and T6 are all threaded together. There we go. And now we've got everything for the dual voltage, low voltage connection. Okay, so again, low voltage means parallel. And you can see here that we're going 1 and 7, the tops are together, right? These guys are together. 2 and 8, 3 and 9 are together. And then in order to create the Y, we have to do 4, 5, and 6. On this diagram, 4, 5, and 6 look like they're all tied together. But in effect, we actually have two Y's that are superimposed on each other, where the center point of each of the Y's are not touching each other. Excellent. Okay, let's take a look at the higher voltage connections now for the Y-connected dual voltage motor. Oh, and just a note before we start in on the series connection. If you're looking at this diagram and then you look at the series diagram and you say, I wonder which diagram they're going to give me on the test. Well, you're going to pick the dirty one. This one is dirty, right? Like this has all these different connections here. If you do a different diagram, like this guy down here, then you'll be able to figure this guy out. But wait till we do the series one. The series one's dead simple. I'm not going to give you the series one. Okay, let's go look at the 416 one. Okay, so the higher voltage. So again, this motor can work off of two different voltages. It can work off of two 8 volts or it can work off of 416. Now in 416 on the higher voltage connection, let's just zoom in here. This guy is going to be the series connection. So anything where it says higher voltage, then that's your series connection. If you wanted the higher voltage output on a transformer, you would connect up the windings in series. And this guy, the higher voltage is coming in. So we're going to connect all of these windings up in series. Now we can rock through the labels on each of these guys, right? This guy is T1, T2, T3, right? And then on the previous diagram, we noticed that they all went up by 3, right? So this guy is T4, up by 3 is 7, okay? 2 plus 3 is 5. 5 plus 3 is 8. Beauty. Then we got 3 plus 3 is 6. 6 plus 3 is 9. And we are done, right? Remember that these guys right here, they're all connected together. But T10, what am I doing? What are you smoking? T10, T11. They're there on the inside of the machine, but there's no way to get to it. This guy, again, is a 9-lead dual voltage motor. Okay, so now what we need to do is we need to do the series connection of these guys. So that simply means that we are connecting up these guys in series. So we're putting a jumper between all these guys. There we go. And then, like any other 3-phase motor, we're going to bring line 1 into T1. Then we're going to bring line 2 into T2. Okay, and then finally we're going to finish this bad boy off by bringing line 3 into T3. To reverse this motor, all we have to do is change any 2 leads, right? Now, this one again does not need a neutral because everything's balanced. The neutral only would carry the unbalanced load. So for a 3-phase motor, you just have to bring 1, 2, 3 conductors. All of the jumpers are done inside of the machine. All right, I think that's everything for the high voltage here, guys. And man, compared to that parallel diagram that we just did, this one's dead simple. So let's just scroll down here to that chart that we have below for our connections. There we go. And now we can see that line 1 is obviously going to T1. Then we got line 2 going to T2. Line 3 going to T3. Okay, and then we've got to join some together. So we got to join 4 and 7. What else do we need to do? 5 and 8. And finally, we need to join 6 and 9 together. Okay, so all of those guys are jumpered together, and that provides us with the higher voltage connections for this motor. Now, this guy is going to give us the exact same horsepower as the low voltage connections that we did on the previous page. Now, the next step is to look at each of the different voltages that are apparent on all of our windings. Okay, so let's stick with this one and we'll walk through this guy. This one was the higher voltage, right? So this one had 416 volts going into, and that would be our line voltage, going into this machine. Okay, we need to find out what the voltage is going to be on each of these windings when we put 416 to the line terminals of the motor. Well, the next step would be to find out what our line to neutral voltage is, right? So the voltage from here to here, right? So let's take that 416 and divide it by root 3. So we have 416 volts. And we're going to divide it by the square root. So I'm going to do second function, this guy, square root of 3. Hit enter. Hey, look at that. 240 volts for our line to neutral voltage. Okay, so this voltage right here is 240 volts from a line connection to the star point of this motor. Okay, but that 240 is not impressed across like each of these guys. Like what I'm trying to say is there's not 240 on each of these guys, right? Kirchhoff's law is that the sum of the voltages will equal the source, right? So that 240 is across 1, 2 windings. Those guys have the exact same number of turns, the exact same gauge of wire, and so they'll have equal voltage drops across them. So we'll have 120 volts across this guy and 120 volts across this guy. So for full marks, guys, if I'm giving you the series connection, or Ted or Steve are giving you the series connection here, then we're looking for everything. We're looking for the diagram containing 2 windings per phase. We're looking for the appropriate labels on each of the windings, right? So the toilet bowl effect, or you're just going up by 3, 1, 4, 7. Remember the 10 is not there, not available to get. So we're making sure that you have 9 leads available, right? And then once you've done that, then we've got the 416 volts going in. My computer is dying a slow death. 416 volts going in, and then we've got 120 volts on each of these windings. Excellent, okay? In addition to that, I better start talking fast. The circle of death is happening here. In addition to that, we got to do all these connections down here in the chart. Okay, now this usually comes at the end of the course. and you guys fail to study this stuff. But it's really depressing at the end when you guys do your test and you don't know how to wire up a dual voltage motor. So go over it now, go over it again a week from now, and then study it again for the test. All right, let me stop my computer for 30 seconds. We'll go back up to the low voltage connection, and we're going to make sure that the voltage on each of the windings is 120 volts again. Okay, so in the series connection, we found that the voltage impressed across each of the windings was 120 volts. So let's see if we can prove the same for the parallel or the low voltage connection. So for the lower voltage, we have 208 volts going into the motor. So we have 208 volts as a line voltage from line 1 to line 2, 2 to 3, and 3 to 1. And that voltage going into the Y. Now, it's a little bit, I find a little bit hard to find or see where the line and neutral connections are on this diagram. So if we just make a line here, right, and a line right here, then we'll see that there is 208 volts going into that circuit. Okay, so that's our line voltage from, in that case, from line 1 to line 3. Now, hopefully you can see that the line to neutral voltage is going to be impressed across each of these windings. And in a Y circuit, the voltage on the, from line to neutral is √3 less than what you have on the outside. So let's take a look at our calculator. We already know what the answer is here, but again, we'll just do 208 divided by √3. Turn this guy on. So again, 208 divided by the square root of 3. And we're going to see something that says 120. There we go, 120.08. Okay, so we can see that the voltage on the phase, right? This will be 120 volts on the phase, and we can clearly see that that voltage is impressed across each of the different windings. So we're going to have 120 volts here, 120 volts here, and we'll have it on every single winding of the motor. Beautiful. So we said that it didn't matter what the voltage going into the motor was, whether it's 208 and we have them connected up in parallel, or whether it's 416 and we have them connected up in series. The voltage impressed across each of the windings is 120 volts. 120 volts here, 120 volts here, 120 volts on each of these guys for the 416 connection. And we've just proven that for the parallel connection, we have 120 volts impressed across each of our windings for the parallel connection as well. Okay, so we've started off doing each of our connections or terminals on the motor, right? So we went T1, T2, T3. We did the toilet bowl effect, or we went up by 3 here. There are 9 leads here. This motor runs on 2 different voltages. For the lower voltage, we connected up everything up in parallel. For the higher voltage, we connected up everything in series. And then we found that regardless of the voltage going into the machine, the voltage impressed across each of the windings is exactly the same. And that follows that the horsepower output would be identical for both the higher voltage or the lower voltage going into that motor. All right, guys, hopefully everything makes sense. If I screwed anything up or if I lost you at any point, then leave me a comment in the comment section below, and I'll see if I can clear it up. All right, guys, what we'll do next in the next videos is we'll take a look at each of the connections on the motor. In the shop, we'll determine whether we have a Y-wound motor or a delta-wound motor, and then we'll hook it up to our 208 volt source and get it rocking and rolling. Prior to that, though, we've got to do the delta connection. So the next video in this playlist will be the dual voltage motor being delta wound. All right, guys, we'll see you in the next video.